Hello, everyone. I'm Steve Kranek. I'm from Some Product, and I'll be introducing our next speaker, Charles Williams. Charles is an independent Excel consultant. He's been that for over 20 years. He's fanatical about Excel performance and extensibility. Uh, he- Charles developed C++, XLLs, and VBA add-ins and solutions, and currently dabbling with JavaScript. He's the author of the Fast Excel Speed Tools multi-threaded function library, Manager Pro, and Name Manager add-ins. And he's been a Microsoft Excel MVP since 2009. So congratulations, Charles. And here we go.
Hello, everybody, and welcome to this session at Excel Virtually Global 2023 on how Excel interacts with Python. Let me start by introducing myself. I'm Charles Williams. This is my 15th year as an Excel MVP. I'm quite a long timer. I have a website that has a lot of information on how Excel does its calculations. That's one of my specialities. And I have a blog, Fast Excel at WordPress, which is full of information about how Excel performs, UDFs, JavaScript, all that kind of stuff. Let's have a look at how these two things interact. So, Excel calculation versus Python calculation. Excel does its calculations smartly. It only calculates the cells that the formulas that it needs to recalculate, and it works out how the formulas depend on one another, builds a dependency tree, and does the recalculation in the dependency sequence. But Python does things completely differently. It calculates the Python cells left to right, top left, starting at the top left, left to right, and row by row. And all the Python cells are what I call co-volatile. That means they, when one of them calculates, they all recalculate. So how do these two completely different animals work together? How on earth does that work? Let's look at that using Excel. Let's start with a very simple example. Here we've got a block of Python cells which just simply refer to one another. And we've got a block of Excel formulas that refer to one another. And that's it. So if we trace dependence for starting with cell A1, we will see that the first Python cell uses cell A1. The next Python cell adds 1 to the previous Python cell. The next Python cell adds 1 again and again. So we can see this zigzag pattern starts at the top left, the first Python cell in C4 here, and then goes across the row to the next Python cell in that row, then down to the next row, and so on. Excel, on the other hand, works completely differently, as we said. So we trace dependence on that. So the first Python cell, first Excel cell, sorry, is referred to there. The next Python cell, the next Excel cell refers to that. But then we've gone backwards to the previous Excel cell, and then we go back up there. So this Excel calculation doesn't care what the sequence of the cells are on the worksheet. It just works it out on the using the dependency tree, and there we go. Now, so if we move cells around, let's see what happens. So we move this Python cell here, and we'll put it over here. Now this is breaking the Python rules, of course, because it's no longer going to be left to right. Ba-boom, it recalculates, and first time Python starts up, you tend to get more of a problem. It says we've got a circular reference because it can't recalculate things left to right because this Python cell refers to a Python cell that comes after it in the Python calculation sequence. We move it back again, it recalculates and everything's fine. And you could actually see it recalculating as we track through. So if we change that cell to a 2, then you can see that the Python cells go click, recalculate, recalculate, recalculate. But if we move the Excel cell to a similar position, nothing happens. I mean, it just works. We don't get a circular reference. So that's the advantage of the Excel calculation sequence. And of course, there are reasons why Python has to do things this way. Python stores things in a global space. So here we've got some Python formulas that don't refer to Excel at all. And the first Python cell says df data frame equals 1. So that creates a data frame and stores a value 1 in it. The next Python cell says let's add 5 to that data frame. And the next Python cell says let's add 10 to the data frame. So we can see we start with 1, we add 5 to get 6, we add 10 to get 16. So if we look at the dependencies, notice these are black arrows rather than blue arrows. So Python dependencies get tracked in a different color to the Excel dependencies. We can see that they are internally dependent. There's nothing to do with Excel here. This is pure Python. If we look at the Excel stuff, okay, let's try that. So that cell has a dependency here, and this cell has dependency there. So that's exactly the same shape of things as Python, but these are Excel formulas. So what happens when we move things around? So we move that Python formula down here. It recalculates and the values change because they're all dependent on this global data frame value. And so we've changed the sequence of calculations. So first of all, we set it to 1. Then we add 10 to it to make 11. And then we add 5 to it to make 16. So we move it back again. The values change again. On the other hand, when we move the Excel cell in the same way, the values don't change because it's internal dependency. Excel is tracking its dependencies and calculating in dependency calculation sequence. And of course, if we move this one to up here, we get a Python error. Whoops, nasty things here. It says df is not defined. Those are two earlier errors. Quirky Python stuff. Now, the problem here is that we've referred to a data frame, but the data frame doesn't exist yet because it's only defined in cell E3, C3. We move it back again with any luck. This will work and recalculate. Yeah, there we go. Now let's look at what I call co-volatility. Here we've got some Excel cells. These are just simply numbers in the cells. And we've got a set of Python cells that just referring directly across to the corresponding Excel cells. So they both give 1, 2, 3, 4, 5, 6, 7, 8. So if we change cell A10, let's put a 9 in there. Python recalculates, and you can see that it calculates top to bottom, left to right, top to bottom, as Python does. But despite the fact that only one of these Python cells is actually dependent on that Excel value, all the Python cells have recalculated. Okay, so, and this happens across the entire workbook. So if you have lots of worksheets with lots of different Python cells on, as soon as you change one, they will all recalculate. So they're co-volatile. One out, all out. Let's recalculate. Okay. Right, the next thing to look at is what happens when you take different types of Excel values formatted in different ways into Python and then return them back to Excel. In other words, let's round trip things, Excel to Python and back again. So here we've got a set of things. We've got a number 1, which is an Excel floating point number. It's formatted as general, and it goes to Python, and Python thinks it's an integer. Well, that's probably not really a problem. When it comes back to Excel again, it's a number again, floating point. If we take a number formatted as number, same thing happens, except this time it's a floating point number. Here's an interesting one. We've entered this number into a cell, and then we formatted it as text. So when we pass it to Python, but of course underneath the format, it's still a number. So when we pass it to Python, Python says, well, okay, it's really a number. So it treats it as a float. When it comes back to Excel again, it's lost the formatting. It's no longer formatted as text. So it's a floating point number. Same way with currency. So I think that's all right, because really the underlying thing is correct. It is actually a float. If we change the format back to a number, now I know what we do. We'll leave it formatting as text, and we'll re-enter it. And in that case, after it's done its Python recalculation, now it's a string. It really is a string because we've entered a number into a cell formatted as text. So, potentially a few gotchas there, I think, if you're not being careful. But that's really standard Excel stuff. Currency works okay. It goes through to Python as a float, comes back as a float, no problem. False, it goes to a Python Boolean, comes back out as false. NA, it doesn't really work in Python because there's no such thing. It's an Excel error. But it manages to go there and come back again okay. This is just a piece of text. That works fine. Comes back out again. This is an empty cell. So that goes through and comes back out again okay. And this is a single space. So it's not an empty cell. It's just a cell with a blank space in. That works okay. Now here's some interesting things. Excel doesn't really understand date and time. So we've entered a number into a cell. In fact, these 3 cells all actually contain the same floating point number. But this one's formatted as time, this one's formatted as date, and this one's formatted as a number. So we pass that to Python, and Python does have a time type. So it becomes a Python time value. And then when we come back to Excel, it's not actually the same value anymore. It's removed the date part. So we've converted something which was a floating point number formatted as time into a Python time type and back to Excel. We haven't got the same number anymore. Similarly, when we take this number formatted as a date, we pass it to Python, it becomes a date time object. And when we come back to Excel again, it's truncated the time part of it. When, of course, we do it as a floating point number, everything stays the same. Now, this is definitely a gotcha. Is it the right thing for Python to do? Probably, because it does have the right date time things. But for instance, if I now change the format of that cell to, I don't know, what do we change it to? General. Okay, so it becomes a number. Now, changing the format of a cell does not trigger a recalculation. So if Python, this cell, Python cell, has not been recalculated, it still thinks it's a time. And when it comes back out again, if we do trigger a Python recalc, this of course will work fine, or should work fine. Get there in a minute. Yeah, it's now become a float and it doesn't get truncated. So I think that's all right, but it's definitely a gotcha. Nasty things unexpected things could happen. So now let's look at what happens when we move slightly more complex structures like tables and arrays into Python and back again. Here we've got a nice simple little table, nothing very special, and we're pulling it into Python, and let's see what happens. So if we look at that, got two ways of doing that. We can extract the data to the cell, and we get that. Or there's another way I quite like doing, which is if you right-click and show data type card, you get this sort of thing, which is slightly better formatted, and it tells us it's a 9x3 data frame. Okay, and we can see that it thinks it's got some headers because we told it headers equals true. Now, if we change that to be, let's get rid of that. If we change that to be headers equals false, be careful with your spelling here, I keep getting this wrong. For Python, it's capital F A L S E. Okay, that should do it. Going away, thinking about it, and thinking about it. Okay, now we've got data frame. Let's see what that looks like. We'll show data type card. And yeah, because we told it hasn't got a header, data frames have to create indexes for things. So now we've got an extra row in the data frame, which is effectively the index to the columns. If we look at it from extract data to a cell using array preview, it doesn't give us the 1, 2, 3, which is kind of interesting. I think that's quite sensible. I mean, whilst it's a data frame, you can actually manipulate it using data frame methods on the indexes. Once you return it to Excel, you haven't got the indexes anymore. So there's nothing much you can do with it. So yeah, basically if we get rid of that and we tell it to go to Excel values, thinks about it again, you can see the flickering on that is because we've got format cells, format dirty cells in action. Okay, so that's just come out as without the additional headers. And if we change it back to true, nothing much is going to happen. Control Enter. Flicker, flicker, flicker. Whilst Python does its calculate things. Of course, we got several Python cells in this workbook, so it's recalculating them all. So again, that comes out exactly the same. We've lost all the formatting, of course. It doesn't know it's a table anymore, but that's kind of what you'd expect. If we convert it back to, let's go headers equals true. Let's go back to having it as a Python object. And what happens if we convert this table into a range? go. Table design. Convert to range. Yes. That triggers a recalc. So we can see the data frame is the Python is recalculating. Now, show data type card. Yeah, it's a 9x3 data frame, exactly the same as it was when it was a table. And if we go headers equals false, whoops, capital F, Control Enter, busy, and then we look at the data type card. Yeah, we got the 1, 2, 3 again. So it's not really treating tables any differently to just ordinary ranges. Now we can also pass into Python named ranges. I've got a dynamic named range called dyname range. So if we change this to refer to that, Control Enter, we should get the same result. Yeah, it thinks it's worked. Yep, it's all there. So that's kind of interesting, because what that says is if we put a formula inside an Excel name, we can pass that to Python. And it will get evaluated before it gets passed to Python, of course, so that the result appears in Python correctly. But there's probably some fancy tricks we could do thinking about that. Now we're going to look at a slightly more complicated case and do a deeper dive into what Excel is really doing with all these linked Excel and Python calculations. What I've set up is a case where we've got a cell in Excel, A10, which is picked up by Python, PY Excel A10. Then we've got an Excel formula in cell E11 that reads the result of the Python cell in E10 and multiplies it by 10. And then finally, I've got another Python cell that reads the result of that Excel calculation and puts it into Python. So a flow, Excel to Python to Excel to Python. What's going to happen here? So let's try, we'll start the calculation sequence by changing the starting cell to a different number. And yeah, we can see everything's recalculating, and now it's done. Now what we've got in these cells are sequence tracing functions. So these show what the sequence in which the cells were calculated. In this cell, we've got a total calculation counter of the number of times Excel is calculated. It started as 1. Since we did the 5, it's gone to 2. And here I can show what happens, the details of the Excel calculation sequence. So we start with a calculation event. It does an Excel calculation. Not surprisingly, we changed a value. We're in automatic mode. That's what we expect to happen. And then the cell A10 says, okay, I've calculated and I put the result in A10 and I'm on sequence 1. So 1 cell has been calculated so far. Now, looking at the next 3 lines, we've got defer calc, E10, E11, and E12. So these 3 cells have all been deferred. Now, way Excel calculation works is if a formula tries to be calculated, but it depends on some other cell that hasn't yet been calculated, the calculation gets deferred down the calculation chain. Essentially, they say, well, okay, I can't do it now, shove it down further, and hopefully by the time we get there, the thing it's depending on will be calculated. So after calculating A10, all these 3 cells were deferred because the first cell is a Python cell. And then we get an event which says, okay, now I want to do a PY calculation. So the Excel calculation has been done, but another event has been triggered that shows a calculation state of pending. So that's the start of the Python calculation. So then what happens is cell E10 gets calculated. That's the first of the Python cells, this one here. So that's the second cell to be calculated. And now the cell E11 can be calculated because the cell it depends on, which is E10, has been calculated. So we say calc result, and that's the third cell to return a calculated result. And at this point, it says, okay, I'm going to defer the calculation of the Python cell in E12, which depends on the cell I've just calculated. So it shunts that further down the calculation chain and launches another Python calculation because we've still got a Python cell that hasn't been done yet. And the result of this is that E12 gets calculated, and it's the fourth result cell to be calculated. 1, 2, 3, 4. And then we get a final event, which is a sort of tidy up. Okay, we put a value back in the cell from Python. Let's do a calculation to see if there are any dirty cells. Wow. It's a little complicated, but you get the feeling that, okay, what we're actually showing is that calculations sort of alternate between Excel and Python and Excel and Python, which is what you'd expect if you're looking at the way the dependencies flow between the different cells. It's interesting that the calculation events also show that you get a calculation pending when there are Python cells to be calculated that haven't yet been done, but we've calculated all the Excel cells. So flip-flop between Excel, Python, Excel, Python. Let's see if that makes sense. And let's try that one more time. And this time we're going to click the Python reset button instead of triggering the calculation by changing an Excel cell. So that should trigger a Python calculation, but there aren't any Excel dirty cells, so we shouldn't really expect anything to be done until we've done a Python calc. Okay, we can see it's doing the same usual kind of thing, calculating the cells. The Excel's calculation counter has gone up to 2, it was at 1. Let's show the calculation sequence results. So it starts by doing an Excel calculation to see if there are any dirty cells. There weren't any, so no cells got calculated. And it says, okay, I've got to defer all the Python cells and the cells that depend on the Python cells, like E11, which is an Excel cell that depends on our Python cell. Because we've got to wait for a Python calculation to occur. So all these 3 cells get shunted down the calculation chain. So then we start a Python calculation, and it does left to right, top to bottom. So it starts with cell E10 and calculates it. Boom. That's the first cell that's actually got a result returned to it. Now, Going down the calculation chain, we've got cell E11. We can now recalculate that because it depends on E10, which has just been calculated. So that's got a value to be worked with. So that's the second cell to be calculated. Then E12, as we scan down the calculation chain, also has to be deferred again because because we need another Python calculation. So then we do initiate another Python calculation that calculates E12. That's the only cell left to be done. That's the third cell to be calculated. And then finally we wrap up with an Excel calculation to check there aren't any more dirty cells lying around that haven't yet been calculated. So the difference this time around was we didn't trigger things from making a change to an Excel cell. We went straight into triggering the Python calc. So what that means is when we started the calculation, there weren't any cells that had been calculated, so we got a calculation sequence of 0 for all the cells that had been deferred. And then as we produced the results for 1, 2, and 3 cells. Okay, so I think we're beginning to see how this works. As I said, it's a flip-flop between Excel and Python and so on as things go down, and it's heavily dependent on deferring calculation of the cells that rely on uncalculated, that refer to other uncalculated cells. Now, ordinarily, this is not a problem. Most Excel formulas or all Excel formulas and all the native Excel functions, whenever they encounter an uncalculated cell, they stop work immediately. This is not true, however, for VBA user-defined functions. VBA user-defined functions get called even when they're deferred. So if you have an expensive calculation inside a UDF, you need to put some code in there to make sure it exits as soon as it encounters an uncalculated cell. And we can look at how that's done. Okay, so let's have a quick look at the VBA that's lying behind this calculation counting and event counting and so on. The main function is this calc counter function. And what it does is it looks at the cell that's being passed to it and says, if it's empty, then this function is going to be deferred down the calculation chain because the the cell that's being passed to it has not yet been calculated, assuming it doesn't point to an empty cell. So we create a message saying defer calc reference address and pass it the calculation sequence counter. Otherwise, it's not an empty cell. This is a result cell. So we increment the calculation counter, create a new message, calculation result, etc. Return the message to the function so that materializes in the Excel cell. If the results array that I want to output has not been initialized, we then redimension it. This is a cunning trick for finding out whether a VBA array has been initialized or not, which I only discovered the other day. Who knows? If not results equals 0, then we can redim it. Then we store the result in the output array. Then there's this is the function that calculates that shows how many Excel calculations have been done. It's a simple volatile function that increments a counter. And then there's a zero calc seq function that gets passed, that gets triggered by that button on the sheet, which resets all the counters in the arrays. And then there's a results array show results thing, which dumps out the array onto the worksheet. The only other thing we've got is in this workbook, we've got a sheet calculate event trap. So that says, okay, let's increment result index and it checks the Excel calculation state. If it's done, then we finish the Excel calculation. But if it's pending, we've got a Python calculation yet to do. And if it's calculating, we'll show event as calculating. It doesn't happen in the tests that we're doing with Python. Then we having created the message, we put it into the results array. So that's it. I mean, it's fairly simple stuff. Just depends on a few basic tricks, like determining whether an Excel cell has been calculated or not. Now I want to look at how to use Python to create your own user-defined functions. I'm going to use a very, very simple example, but of course in practice, the occasions when you'd want to do this are probably more when you want to access some of the incredibly powerful Python libraries and embody them in a user-defined functions to simplify the use of these functions. So let's look at how we define a function. In this cell, let's drag that down a bit. I'm defining the function. So def mysum df1 df2, and the description of this is it adds two numbers, and we define df3 data frame 3 equals data frame 2 1 plus data frame 2, and then I return data frame 3. Now on the bottom of this function I've got a description of the syntax, just so that when you're looking at it in Excel, it's easier to see what it's doing. Now this function gets defined in the global Python space, which we've talked about earlier on. So that means that it needs to be defined before you use it anywhere in Excel. And then when to use it in Excel, we can see here, we just call the function mysum, that's what I called it, and we pass it the values from Excel. In this case, these two values. And of course, we can drag that down to, and it will automatically adjust to reflect the values in the other two cells. Now, there are some pros and cons to this approach. The great news is you've got access to all the Python libraries, fantastic stuff. And the downside is there's quite an overhead associated with this method of calling things. You've got to pass the data that the functions are going to use up to Azure in the Sky, so that Python can do the calculations on them, and then the results need to get returned. And this means that if you have a large number of calls to a user-defined function, or if you've got huge amounts of data you're passing, this may or may not be a suitable thing to do. I think the main advantage is if you have a function that you want to use a few times in an Excel worksheet, you can encapsulate it in a Python function and call it like as we've done here. Or if you want to make use of those powerful libraries. One other downside is I don't see how to make this into a function library which is available to other people to use. Maybe there's a way of doing it, but I don't know what it is yet. Anyway, there you go. Python UDFs. The final example I want to look at is what happens with larger amounts of data and exploiting some of the functions of Python. Example I've chosen is doing a join between two sets of data, 250,000 rows. And I'm comparing an XLL C++ UDF, which is pretty efficient, runs locally and all the rest of it, with a data frame join. And data frames in Python have an incredible number of quite powerful methods implicit in them. And they're really quite easy to use once you start getting the hang of the thing. So let's run a comparison. We'll start by changing this value here. That will trigger a calculation for both the Excel and the Python. We can see that the Python is chuntering away. The Excel bit has finished long ago. Okay. Now we've finished. The XLL function, if you time it, takes around just over 1 second on my laptop to do the join between 250,000 rows of data and another 250,000 rows. Overall, the Python data frame calculation takes around 4.5 seconds, but around 7 seconds if you want to return Excel values. Obviously, that's a lot of extra data. It's going to have to dump back to Excel rather than just simply containing them internally in a Python data frame object. I've also done some timing, built some timing into the Python calls, Python code. So we import time. We take the start time, time.time. We do the data frame business of getting the data into data frames, do an end time as the current time minus the start, and print that out. So that's the first value that gets printed here. So it took 1.03 seconds to create those data frames from the data from Excel. And then we do the actual join, an inner join on 2 data frames, and return it back to Excel. Again, looking at the time it takes to do the actual join on the data frames. The actual time to do the join is pretty fast. It's 1.2 seconds. It's very comparable to the C++ XLL doing the join. But of course, there's more times you have to move all the data, which is quite a lot of data. You know, you're talking 500,000 rows of data in total. It has to be moved up to the cloud. Then you do the calculate. Then you turn them into data frames, and then you do the join, and then you send the data back in a data frame object. So I think this is an example of what's both good and bad about Python, is the Python and Excel implementation. Great news is, you've got an awful lot of power. It's very easy to use. It's all packaged nicely. It works well. The downside is it's in the cloud rather than local. So if your data is local, which it will be, you're going to have to send the data up to the cloud. That could be an overhead, depending on the speed and the amount of bandwidth you've got. And then you've got to bring the results back to Excel, which again is another overhead. So you can see that overall, the 2 times added together are only 2.2 seconds, but the actual total calculation time for that function was 4.5 seconds. So there we go. So let's wrap this up. We've looked at how the interaction between Excel and Python works in quite a lot of detail. We've discovered some of the gotchas and some of the good things, different stages of calculations. And really, I think it's become obvious that if you want to use large numbers of PY cells, performance is not going to be great because of the sort of co-volatility overall of Python cells. And, going from Excel to Python to Excel to Python and so on, not terribly good idea. It works okay. But I wouldn't want to build a whole lot of calculation chains like that. We can do UDFs, but there's some limitations on them. I think for me, the real good points about Excel and Python are, it's really much easier to use than having to set up your own Python, install it, etc., etc. Your integration with Excel is terrific. And wow, we've got all those fantastic Python libraries. So it's great stuff. Okay, this is early days. I can see that hopefully there are some future improvements to come, but what we've got is really exciting. Now, here's an evaluation slide if you want to, if you've liked what you've heard. If you haven't, don't bother filling it in. And the Microsoft Excel team is looking for research participations if you want to grab a hold of that. So thanks everyone for listening. Hope you enjoyed it. Bye.